Hello, class. Alright, so sorry about today. I had an appointment earlier that took longer than expected. So I initially thought I'd get back in time, but actually I was only about 5 minutes late. But I'll do like a quick review on torque, and then I'll just go over the suggested problems. So in the recording, we considered a coil that was a square because that's just a very convenient shape. So, it's one wire. In this case, it just makes one loop. And so the current, looks like that. So it comes in, loops around, comes out. And so if we're in a magnetic field, then depending on the orientation of the coil in the magnetic field, generally there will be a torque on this coil due to the magnetic field. Now, we know that there's a force on a wire. Let me just write that down. So in a magnetic field, there would typically be forces on these wires, and if it's free to rotate about this axis, there could be a torque due to these forces. And again, I went over this during the recorded lecture, so we'll kind of skip most of that and just jump straight into defining the magnetic moment. And again, we showed that for let me finish this. The magnetic moment is NIA, where N is the number of loops. So if we, loop the wire around multiple times, we get a greater torque. There'd be a torque on each coil. So if N loops, we'd have N times the torque. I is the current, and A is the area of the coil. And we showed that for a square, this gives the right torque, just for a square coil. And we did that because it's very easy to calculate. But let me write down the actual torque then. Now, torque is a vector, but the magnitude of the torque is the magnetic moment times a magnetic field times the sine of the angle, and I have to define what that angle is. So first off, the magnetic moment is a vector as well. And it's perpendicular to the coil. So like here, our coil is, in the plane of this board. And so a magnetic moment is perpendicular. So, if we have a perpendicular line going through, it's in the direction of that line. But again, we have to distinguish, what direction is it? Is it going into the board or out of the board? And we use a right-hand rule for that. So you curl your fingers around in the direction of the current. So here, the magnetic moment would be out of the board. If we reverse the direction of the current, it would be into the board. And then in general, say we have a coil. So we have a magnetic moment, say in this direction, and say a magnetic field here. Theta would be the angle between the magnetic field and the magnetic moment. Those are both vectors. And so now we know what theta is. We can find the magnitude of the torque. What about the direction of the torque? Well, it's going to want to rotate the coil so that the magnetic moment lines up with the magnetic field. So we've got the magnitude and direction of torque. And it's really nice to break things up. We calculated the torque directly just based on the forces on the wires and the definition of torque. Well, it's nice to kind of split it up into two pieces where you have the magnetic moment, which again, this is a property of the coil itself. It depends on the number of loops in the coil, the current going through it, and the area of the coil. And then we have an external magnetic field, so torque is a combination of those two things. Again, we always showed that this is true for a square. Most coils that we would deal with in practice, though, are circular. So, if you remember how we showed this result here, just based on forces on wires and directions of currents, that would be rather complicated to do so in the case of a circle or any other shape. There is one other shape, though, where it's not too bad to calculate the torque. We're not going to actually do it, but say we have a triangular coil. And if we were to calculate the torque just like we did for the square, we would find out that the magnetic moment is NIA again, where A is the area of this triangle. And really, we can use that fact, just like a square and a triangle, or you could also do a rectangle more generally than a square. But say we have a circle, that would be a much more difficult calculation. But we don't really need to do anything new here, because what we could do, let's draw a square like this. Let's say that our circle, we have a current going around in this circle here. So let's start out by drawing a square inside that looks like this. And then say above here, now we can make these very close together. I'm just putting a little gap between them for so we can see what direction the currents are going. And maybe in this area here, let's draw a triangle. And again, we would do the same here. And imagine we do this kind of all the way around this central square. So we'd have one here. We'd have a little rectangle here. Triangles and all these kind of gaps. And the effect of all of these currents that we've built up, we've got like all these objects inside, but effectively it would look a lot like this circle. If you look at this area, see we've got a triangle here as well, where the current's going this way, looping around that way. And if you go around here, you've got like this current going to the right everywhere here, and a current going to the left. Those two basically just cancel each other out. And same here, like all these interior regions, we have these currents going in opposite directions, and so they just cancel out. The only currents that don't cancel out, like here, this one's going up, that one's going down. The only ones that don't cancel out are on the outside. So we know that the magnetic moment of each of these, they are just the current times the area. We have a single loop. And so effectively, by building this more complicated thing, we get just the outer loop. The magnetic moment would look, just like this outer loop. We'll do this in red or something. So we could get something like that, where the magnetic moment would follow this formula. And that's fairly close to this circle. And we can make it better by just adding more rectangles and squares. So if we put a smaller one here, we can, and then we put a triangle there. So again, we can get closer and closer to the circle by adding more square or rectangles and triangles in the interior. And if you just repeat this process enough, you get as close to a circle as you want. And so this formula here for the magnetic moment, that applies to any shape. Okay, so the topic today is just calculating torque on a coil due to a magnetic field. So I want to go through the suggested problems then. And then we'll do a real quick review on Friday as well, in case you have any further questions. Try to get back on track then. But, let me just go through these. So problem 1, we have a circular coil with 60 turns and a radius of 1.5 centimeters. So now we just want to find the magnetic moment. We're also given a current. Okay, so yeah, that was also given. So again, this is just simply plugging things in. So we have 60 turns. Current is 5.1 amps. And the radius is 1.5 centimeters. So let's convert to meters. Typically, magnetic moment is in amp meters squared. So let me just get a number. I'll check the answer key on edit. All right, so I'm getting 0.069 amp meters squared. The answer key, I might have left it as amp centimeters squared. This is wrong. The area, I did Ni times R squared. Forgot the area of it's a circular coil, so the area is pi r squared. So if we multiply that, then I'm getting the same answer as the answer key then. That would be 0.22 amp meters squared. Okay. So that one is a pretty straightforward calculation. Well, I meant to screw it up anyways, but there's 8 problems to go through, so I want to go through these reasonably quickly. Okay, so to go on problem 2, a coil with a magnetic moment would be 2.14 times 10 to the minus 3 amp meters squared. It's in a magnetic field, 55 milliteslas. What is the maximum torque that this coil can experience in that magnetic field? So again, the torque is magnetic moment times magnetic field times the sine of the angle. And the maximum value sine of theta can have is 1. That's when there's a 90-degree angle. So we'd have a situation like this where the magnetic moment is in one direction and the magnetic field is perpendicular to that. In that case, that would give you the maximum torque. So let's calculate. And again, we want to get Newton times meters out of this. All right, so we have 2.14 times 10 to the minus 3. So we'll put that on the bottom. The magnetic field is 55 millitesla. We're going to put this up higher. Okay, so the tricky part, of course, is getting the units right. So then we can do this. We can see from that top equation that a Newton is an amp times a meter times a Tesla. So Newton, and yeah, it looks good. So I think that'll be it, actually. Let's do a Newton over an amp times a meter times a Tesla. And I think we can just cross off. So yeah, we're left with newtons times meters. So let's do 2.14 times 55. So I'm getting 117. Let's say 118. And then times 10 to the minus 6 Newton meters. Or 1.18 times 10 to the minus 4 Newton meters. Yeah, I wrote down 1.2 times 10 to the minus 4. Two significant figures, but yeah. Okay, so again, fairly straightforward calculation. Okay, now, all right. Problem 3, a circular coil with 100 turns carries a current of 1 amp, radius of 5 centimeters, there's an external magnetic field of 0.2 millitesla, and the angle is 35 degrees. Yeah, it says an external magnetic field of 0.2 millitesla makes an angle of 35 degrees with respect to the magnetic moment. So again, you always want to make sure when you have a theta in a formula that you're using the right theta. Yeah, that's the case here. So what is the torque on the coil? So let's first find the magnetic moment. So the area, it's a circular coil, so the area is pi r squared. So let's plug in the numbers. So we have pi. Let's put that first. N is 100. Let's do this. Okay, so that's N times pi. The current is 1 amp. So we have Ni pi, and then the radius, say 5 centimeters, so 5 meters over 100, and we square that. So 5 squared is 25. So we have 100 squared on the bottom. We can cancel out one of those. So we have 25 pi divided by 100. So it would be an amp meter squared. So 0.79 or 785. an intermediate calculation, so we'll round off at the end. But yeah, 0.785 amp meters squared. And now the torque we have the magnetic moment. The magnetic field is 0.2 millitesla. So it's a 2 Tesla over 10 to the 4th power. So 0.2 over 10 to the 3rd power, or 2 over 10 to the 4th. And then we want to take the sine of 35 degrees. I'm just going to do that by itself. Sine of 35, again, you always want to make sure you're in the right mode. Sine of 30 is 0.5, so we should be close to that. Yeah, I'm getting 0.57. Yeah, so if you're in the wrong mode, you have some idea what you're expecting before plugging it in. Good idea. And now it's the units. So yeah, and we'll probably just keep using this conversion factor. So a Newton is an amp times a meter times a Tesla. So there's amps. Cancel out one of the meters. And so yeah, we get torque in Newton times meters. So numerically, I'm getting 0.9 on top. And then, divided by 10 to the 4th. So torque would be 9 times 10 to the minus 5th power. Newton times meters. Okay. So, yeah, that's what I got in the answer key as well. Okay, so let's get to, again, these have been just calculations so far, for the most part, pretty straightforward. Let's get to problem 4. So here, so the coil has a magnetic moment. Of 6.4 times 10 to the minus 4 amp meters squared. It's in a region with a magnetic field. (3.5 times 10 to the minus 4 Tesla). The angle between the magnetic moment. I'm going to make sure I read this carefully. Okay, yeah, the magnetic field and the magnetic moment make an angle of 25 degrees. So what's the torque? So essentially it's the last problem, except we're actually given the magnetic moment. So again, this is just plugging things in, so let's just do that quickly. We'll use the same conversion factor. There's magnetic moment. Magnetic field. And I'll take sine of 25 degrees. 0.42 looks about right. And then a Newton is an amp. And again, we'll get the exact same cancellation as before. So let's do this. So what I'm getting is 9.5 on top and then 10 to the 8 on bottom. Yeah, so a very small torque in this case. So that was problem 4. Yep, getting the same thing. Okay, So a lot of kind of repeating the same thing. Doesn't hurt to do that. Now, problem 5, we have a circular coil. It's a radius of 6.5 centimeters. Contains 110 turns. And the current is 3.5 amps. What is the magnetic moment of the coil? So let's find the area first. So the radius is 6.5 centimeters, or 6.5 meters over 100. So I'm getting 133 times 10 to the minus 4 meters squared for the area. And we want the magnetic moment. So there's 110 loops. Current is 3.5 amps. And then the area. So we'll get amp meters squared out of this. So let's see. So I'm getting overall 5.1 amp meters squared for the magnetic moment. Just check. Yeah. Oh wait. Sorry. I think I actually made a mistake in the answer key. Sorry, give me 1 second. Okay, so the area, pi r squared, that looks right. Trying to double check since the numbers, just the exponent. Yeah, I'm getting 5.1 amp meters squared. In the answer key, I wrote amp centimeters squared for some reason. So I make a note of that. All right. Okay. Okay. So that was problem 5. So 3 to go. All right, problem 6, something a little different, not much, but now we have a square coil. Let's see. The length of each side is 6.5 centimeter, or 6.6 centimeter. There's a current of 1.6 amps. And we want the magnetic moment. So the magnetic moment, it doesn't say anything about the number of loops, so that would just be, there's one loop. So we just have the current times the area. So we have the area of a square coil, would just be L squared. So we have 1.6 amps times, we'll convert to SI, the basic SI units. So 6.6 centimeters. So we have basically 70 times 10 to the minus 4 amp meters squared. Or 7 times 10 to the minus 3 amp meters squared. All right. Now let's look at problem 7. So again, this one has a picture with it, but it's basically very similar to what we did. We have a single loop with a radius of 1 meter, so it's actually going to be a fairly large coil. But it's a single loop. And it shows a magnetic field as well. Not really necessary, but because of the way the question's worded. But again, this is a situation that would produce maximum torque, because a magnetic moment would be perpendicular to the board, so the angle between the magnetic moment and the magnetic field is 90 degrees. Okay. Picture wasn't really necessary in this case, but let's see. So anyways. So the current is 10 milliamps. Magnetic field is 0.5 Teslas. So what is a magnetic moment? So I need to start with the area. So it's N, magnetic moment, NIA, like putting constants in front. So yeah, the area is pi r squared. So let's plug things in. Oh, it's a single loop, so we have pi, the radius is 1 meter. So that's pi times the radius squared, and then we have, say, 10 amps over 1,000. 10 milliamps. So basically, we don't need a calculator for this. Pi times 10 over 1,000, so pi over 100. So 0.0314 amp meters squared. So that's the magnetic moment. And then what is the magnitude of the torque? Oh yeah, we did need the picture kind of. I thought it was asking the maximum torque, but no. So yeah, we need to know that they're perpendicular. So the torque is just going to be the magnetic moment. I'm going to write it this way, and how it was above. So that's the magnetic moment, and the magnetic field is 0.5 Teslas. And then we have that conversion factor. We've done that a few times. You can even see without crossing anything out. We'll get Newton times meters out of this. So we have pi divided by 200 basically. So I'm getting 0.016. Amp meters squared. So we'll just check both of these. Yeah. Or not amp meters squared. Cross all that out. Yeah, this part is torque. So Newton times meters. Okay, so one more for the suggested problems. So here, this one is a little bit different than the others. Finally, something different. We have a very big triangle here carrying a current like this. So again, it's a big triangle. It's, the smaller side is 2 meters long. Be a pretty large triangle, and there's a magnetic field in that direction. So again, the magnetic moment into the board from that second right-hand rule. So curl your fingers in the direction of the current into the board, and so it's a 90-degree angle. And what would happen here, if it's free to rotate about, say, this axis here, it would rotate this way. So the coil would rotate that way to line up the magnetic moment with the magnetic field. That'd be the goal. Okay, so let me read the problem now. Yeah, so it can rotate about this axis. The current is 4.7 amps. Magnetic field. It's an extremely large magnetic field, 1.8 Teslas. So we want to know magnetic moment and the torque. Now again, just to be clear, when we find the torque, we're talking about the initial torque. But if it's allowed to rotate, it's going to rotate, and then as soon as it starts to rotate, the angle changes, and so the torque would decrease until it reaches 0 when they are aligned with each other. So we're calculating the torque just in its orientation here. So to start with, let's find the area of this triangle. So that's 1/2 times the base, which is 2 meters, and then the height, which we have to define using this triangle. So here we can just say 1/2 base times height, where from this triangle, we want tangent So tangent would be h over 2 meters. So let's do tangent of 55, 1.43 looks about right. And then times 2. So the height is 1 meter, or the height is 2.86 meters. And so if we multiply that by 1/2 times a base, that's just a, that 1/2 times a base is just a meter. So we would have 2.86 meters squared. And now the magnetic moment, one loop, so we have 4.7 amps. Times 2.86 meters squared. So I'm getting a magnetic moment of 13.4 amp meters squared. And that's part A. Now we want to find the torque. And again, they're perpendicular. So sine of theta is 1. The magnetic moment, magnetic field perpendicular. So we would just have the magnetic moment times the magnetic field, very large magnetic field, and then our conversion factor. It's the only conversion factor we needed for this whole thing. So let's do this. So we're finally getting a significant torque here, about 24.2 Newton times meters. Okay, so let me check the answer key. Okay, so yeah, those are the suggested problems. And yeah, sorry about class today. I thought that my appointment was going to run long and I'd be late. And I would have been a couple minutes late, but you would have probably stuck around anyways. So, yeah, hopefully this is enough just going over the suggested problems. And, you know, you can always ask, yeah, we'll kind of catch up on Friday then, if there's any like additional questions or anything. But hopefully we can get back on schedule quickly. So I think I'll end it here, and then I'll see you on Friday.